Okay, this video is dedicated to William, and we're gonna discuss the proof of the chain rule. We might not actually carry out the proof, but we'll discuss it in such a way that will make it clear what we're trying to prove and what kind of issues arise in the proof. Okay, so the proof of the chain rule is a little bit trickier than, say, the proof of the product rule, and we'll see why. So what is the chain rule? So if you remember the product rule tells us how to differentiate a function obtained from multiplying two functions. Well, actually multiplying functions is not the most natural operation on functions. Actually, composing functions is the most natural operation on functions. And the chain rule tells you how to differentiate a function obtained from composing two functions. Okay, so what I mean by composing two functions, for example, if I do f composed with g, okay, and let this function be called k, then what it means is, well, first of all the outputs of g have to go into the domain of f, and so it makes sense. And what happens is, anytime you have an input value in the domain of g, okay, it goes first through the function g, and outputs g of x, and then this output is then fed again into function f. To produce the final output, and this final output will be the output of k. Alright, so if we take some point a in the domain of g and it feeds into the domain of f under g of a, then we say that k prime of a is equal to f prime of g of a times g prime of a. So we're saying if g is differentiable at a and f is differentiable at g of a, then k is differentiable at a, and the derivative is given by the product of these two derivatives. Okay? So that's kind of interesting. It's kind of like what you might have thought the answer to the product rule was, if you didn't know that the product rule wasn't just simply the derivative of the products. Okay, there's an addition involved. But the chain rule, it's kind of like composition. The derivative of the composition is just like the product of the derivatives in some sense. And the composition is a very natural operation of functions, whereas multiplication maybe not as natural. Well, multiplication is just composition in another sense if you think about it. Okay. Now maybe we could try to prove it. Okay, and just at least to remind ourselves what it is these are defined as and what maybe needs to be proved. So the definition of k prime of a involved a limit. Okay, and the limit is what we're saying exists. So the limit is of, by definition, k of a plus h minus k of a over h, which is equal to the definition of k is f composed with g, so this is just equal to f of g of a plus h minus f of g of a over h. Okay. And now if we wanted to sort of mimic the solution, we could maybe try to do something like this. Okay, but I put a question mark here because I'm not claiming it's actually the right thing to do, but maybe it's something That would be nice if we could do it. Okay, and the reason it'd be nice if we could do it is because the second term now, you notice we just actually added the same thing to the top and bottom. So, we would be allowed to do this if this was not 0. Okay. And if we could do it, it'd be kind of nice because now that this term is exactly this g prime of a, the derivative of g at a, that we want in the answer. Okay, and then maybe a little bit of imagination could let you convince yourself that this expression is maybe the limit definition of this term here. Okay, so that would be kind of nice if that was what happened, and then that would be the end of the proof. Okay. Well, the end of the ideas part of the proof. There would still be some hopefully detailed working. Now, but the problem is this can't be done if the bottom is 0. Okay. So, but what can we have? Okay, maybe we could think about how h approaches 0. So instead of having h continuously approach to 0, we can think of h approaching 0 via sequence. Okay, so we can think of a sequence of values of h that eventually tends to 0. For example, h could be the sequence of reciprocals. So it could be like 1 over 1, 1 over 2, 1 over 3, 1 over 4, and so on. You know, you eventually get to 1 over a million, 1 over a million and 1. Those can represent h going to 0 in a particular way. And if this limit exists, then it should be equal to any limit along any sequence. Okay? So maybe imagine, so the problem we had was if this was 0. So the problem is maybe some values of h have that g of a plus h is equal to g of a. Okay, and having h getting closer and closer to 0, you know, may remove these kind of problem h's, but they also may not. So if you always have some h, no matter how close you get to 0, such that this is equal to 0, maybe you could let those values of h be your sequence of h approaching 0. And if you do that, you'll see that actually from here, before we did anything funny with this denominator, along that sequence of h's, g of a plus h is equal to g of a, so f of that will also equal to f of this. And so the limit will have to actually be 0. Okay? And also here, the definition of g prime of a, the numerator will be identically 0 as well, along that sequence of h's. So actually, if you know the limit exists, then when such a sequence of h's giving you zeros here exists, then you know that we're actually proving, have that the left hand side is equal to 0 and the right hand side is equal to 0. So the formula holds. So if we assume the limit exists, then the left hand 0 and the right hand side 0, which is satisfied. Okay. Now, if we can't find such a sequence of h's such that the denominator is always 0, which means eventually we'll get close enough to 0 that all the h's will produce non-zero values of this. Well, then in that case we can definitely just do this kind of thing, because we don't run into the problem of 0 anymore. And if we do that, then this will actually lead to the proof of this formula. Okay, and it will actually lead to the proof with the existence, because we're actually evaluating these limits. So before we even really prove the chain rule, what we have is that if this denominator is a problem, then we basically need to show the limit exists. And if the limit exists, then the formula will be satisfied because both sides will be 0. Okay? If the denominator is not a problem, then this will show that not only the limit exists, and it will show that it'll be given by this formula. Okay? So that's a pretty long discussion. I hope you can follow the reasoning, but at least it'll tell you what kind of issues there are with the proof of the chain rule. And then you could find the proof of the a proof of the chain rule in lots of textbooks and stuff. So this just kind of explains what it is that you're achieving with the proof.